Hi everybody! So in today's video, we're going to be going through the lesson for task 3.6, which is going to be about the idea of a function. Now we have two learning targets for today. The first is I can identify if a representation is a function and support my reasoning. So I'm going to give you several varieties of representations and you need to tell me is it a function or not, and how do you know for supporting your reasoning. The second learning target for today is I can write the equation of a linear function given multiple contexts. So again, this is very similar to what we did on the previous lesson where we are going to be writing equations of a linear function using a point, a slope, 2 points, or possibly a graph. Okay, first let's start with the idea of function versus not a function. Whenever there's a relationship between two ideas or variables, for example, distance and time, we always say that that's called a relation. Now, a relation could be a function or it might not be a function. A relation is considered a function if every input corresponds to exactly one output. In my mind, what I always think to myself is that each input can only go to one party at a time. So each input can only go to one party, which is like the outputs. Now, we're going to need to be able to decide if we have a function using a variety of representations. So the different types of representations that you might see are tables, graphs, a list of ordered pairs, or a mapping diagram. Let's start by looking at a table. So in this example, we're going to see one example where we have a function and one example where we do not have a function. An example of a function would be, or an example of a problem you might see where you have to decide if it's a function or not would be this one. So what we need to think in our head is that 2 is going to 1's party, 3 is going to 2's party, and 2 is also going to 4's party. Well, our rule is that every input can only correspond to one output. However, in this problem, 2 is trying to go to two different parties. It's trying to go to 1's party and to 4's party. So we would say that this is not a function. In the second table here, 2 is going to 1's party, 3 is going to 2's party, and 4 is going to 3's party. So each of our inputs is only trying to go to one party tonight, which means this is a function. Now we can use this same thinking when we have a list of ordered pairs. So in this list, we have 0 going to 2's party, 1 going to 3's party, 2 going to 4's party, and 3 going to 5's party. What that means is that each of our inputs is only being mapped or going to one party. So for this example, we would say that this is a function. In the next example, we would see 0 is going to 2's party, 1 is going to 3's party, 0 is also going to 4's party, and 3 is going to 5's party. As you can see, 0 is trying to go to too many parties. It's trying to go to the 2's party and the 4's party. So we would say that this is not a function. For the next example, let's look at these mapping diagrams. In here it says that 0 is going to 2's party, 5 is going to 3's party, and 5 is going to 4's party, and 10 is going to 5's party. Well, as you can see here, 5 is trying to go to too many parties, so we would say that this one is not a function. In this next example, we've got 0 going to 2's party, 5 going to 3's party, and 10 going to 5's party. So that's okay. They're each only going to one party, which means that this is a function. The last type of situation is when we need to look at a graph. And when we need to look at a graph, here's how we check how many parties we're going to. To check how many parties the number 1 as our input is going to, we need to look up and down in a vertical line and see how many times it touches the graph. In this case, because the 1 has 2 corresponding points on the graph, the 1 is trying to go to 2 parties. The same thing happens if you check the 2. There are 2 places where the 2 has an output value. The 3, the 4, and the 5. As a matter of fact, this is going to happen all the time. A lot of these numbers are going to go to 2 parties. We call this the vertical line test. And the only time you need to use this test, it's kind of a visual test, is when you're dealing with a graph. For the other problems where you have a set of numbers, it's easy to just check to see where each of the numbers is going. But when there's a graph, you need to kind of imagine these vertical lines. Because we only want to have each input go to 1 party, each of those vertical lines should only cross the graph 1 time. Because each of these vertical lines crosses the graph in 2 spots, we would say that this is not a function. Now on this graph, if we imagine drawing those vertical lines, you can see that each line only crosses the graph in 1 spot. And that's going to continue to happen no matter where you draw those vertical lines. So this graph is a function. All right, let's try some practice problems. So in addition to determining whether you have a function or not, you're also going to be asked to explain your reasoning. So we're going to practice identifying if it's a function or not, and also how we would support our reasoning. When we support our reasoning, we're going to go back to the definition. We are going to have a function if every input corresponds to exactly 1 output. And we're going to say that it's not a function if it fails that test. Let's take a look at number 1 here. 2 is going to 3's party, 2 is going to 5's party, 9 is going to 7's party, and 9 is going to 3's party. As you can see, we have 2 different issues here. 2 is trying to go to too many parties, and 9 is trying to go to too many parties. 2 can't go to 3's party and 5's party, and 9 can't go to 7's party and 3's party. So we would say that this is not a function. To support our reasoning, we would say the input 2 and 9 both have more than 1 output. If you ever have more than 1 output, you're not a function. For problem number 2, in order to check if a graph is a function or not, we need to imagine drawing vertical lines. So if I draw a vertical line here, it only touches 1 point on the graph. If I draw a vertical line here, it only touches 1 point. If I draw a vertical line here, it only touches 1 point. If I draw a vertical line here, it only touches 1 point. And that's going to continue to happen no matter where you draw your vertical lines. They're only going to touch 1 point on the graph. That means that we do have a function. And we would say because each input has exactly 1 output. And that again goes back to the definition of what makes these functions or not. For problem number 3, 1 is going to 2's party, 5 is going to 6's party, 7 is going to 2's party. So everybody's only going to 1 party. That means that we have a function, and we would say because each input has exactly 1 output. You'll notice it's the exact same reason I wrote here. So when you have a function, the reason is always going to be because each input has exactly 1 output. For problem number 4, we're again dealing with a graph, and so we're going to use that vertical line test. So if I imagine drawing vertical lines, each of these lines that I'm drawing only touches the graph in one spot. And that's going to continue to happen no matter what. You're always only going to touch the graph in one spot. So this is a function, and we would say because each input has exactly one output. Again, that goes back to the definition of a function. If you have a non-function, then you need to be specific about which inputs fail the test. So in this case, we said because the 2 and the 9 both have more than one output, which is not allowed. Last but not least, we're going to look at applications of functions. So functions are often used in applications in the real world. Some relationships in the real world can be represented with a function, and some relationships would not be functions. Here are some examples of functions. If you put money in a vending machine, and you get one beverage for your money. That's an example of a function. So if you put money in, $1 in, you get one beverage out. If you wanted another beverage, you'd have to put a new dollar in. So one input gets you one output. Another example of a function would be if you are, or here's an example of a not function, sorry. An example of a non-function would be if you made a list of cities and their baseball teams. The reason that this would not be a function is because some cities have more than one baseball team. So that would not be a function. Another example of a function would be if you were measuring or if you were keeping track of the day of the week and the number of hours you slept. There's no way that you can sleep 7 hours on Tuesday and also sleep 11 hours on Tuesday. So each day is going to have one value for the number of hours you slept. Another example of a not function would be if you were going to make a list of the day of the week and your classes that day. Because on a certain day, you might have more than one class. You might have had, math as well as, fine arts as well as history or something like that. So let's take a look then as we look at applying functions in one of the ways that functions are applied, and that is we use equations to describe functions. So for example, for problem number 1, we're asked to write the equation, which is also something we reviewed in our previous video. We know that in order to write our equation, we're going to need to know the slope. And to find the slope, we're going to need to do change in y divided by change in x. Now, change in y here would be going from like 7 to 11, which is plus 4. And change in x here would be going from 7 to 8, which is plus 1. Now, 4 divided by 1 does simplify, which means we get 4 for our slope. To write this equation, we would start with y equals, and then we would use our starting value, which is -1, plus our slope, so +4, parentheses x, and then we need to look at our starting x value. In this case, it's a 5, so to get back to 0, we would put -5 here. For problem number 2, I personally think it's going to be much easier to do this problem if we make a table of values first. So we've got x and y. The first point here is going to be the one that's farthest to the left because we always read graphs from left to right. So it would be 0, 15. Then we've got 1, 13, 2, 11, 3, hold on a second, 2, 11, yeah, 3, 9, oh my gosh, I lost track of where I was. 3, 9, 4, 7, and 5, 5. To find our slope, we have two different options. We can do change in y over change in x again, in which case we would get -2 divided by, from 0 to 1, it would be +1, which simplifies to -2. Or we could look at our graph and we could say that we are going down 2, right 1, so rise over run would be down 2, right 1, and we would get the same answer that way. Oops, I reversed those colors. I apologize. Down 2, right 1. There we go. And we would get the same answer that way. Now, when we write our equation, I do think it's easier to have the table. So we would start with y equals our starting value, which is 15. And then our pattern, which we figured out is -2, parentheses x. And then we would go back to our starting x value, which is 0. That means we don't need to adjust the x to get back to 0. It just already is 0, so we're done. Last but not least, if we want to write the equation of a line that is passing through the point 2, -5 with a slope of 3, then we're going to have x and y. Our point that we're supposed to write down is 2, -5, and it's telling me in the directions that the slope is 3. So to write our equation, we would write y equals our starting y value, which is -5, plus our slope, which is +3, parentheses x, and then our starting x value is 2, so we need to put a -2 to get back to 0. All right, thank you guys so much for watching. I hope that you have a great day, and I will see you soon for some practice.